Hey, how's it going? Terry Brown, Mechanical Engineering here to go through another engineering mechanics fundamental problem. So let me share my screen and we'll get started. All right, so this is the problem. Simple rigid body equilibrium problem. We have a rigid body with a load applied and some constraints here. So first thing we need to do is to draw the free body diagram. And then once we've done that, then we can solve for the unknown reactions at the supports. Hopefully by now you know that when we draw a free body diagram, that the free means that it's free of everything it's connected to. So when we draw this diagram, we don't draw these supports on here. What we do draw, however, are the reactions that are developed by those supports. Okay, so start with just a simple outline of the object that you're wanting to analyze. So it's just this L-shaped thing. We've got a force of 300 newtons applied at that right-hand corner over here at an angle of 50 degrees to the horizontal. And I've already started with the solution here. So at A, what have we got? We've got a pin connection. Okay, so at a pinned connection, this type of connection prevents the object from translating. Okay, so it can't move as a rigid body to the right and it can't translate as a rigid body upwards, but it can rotate about point A. So there's no moment reaction, but we do have two force reactions here, horizontal one and a vertical one. The other way that we could represent this, it would be that we have a single force at some unknown angle or unknown direction. Okay, but usually we'll just put the two components here like I've done. The next thing we'll need to work out is the arrowheads to put on here. Which sense are these forces going to be? So you can just assume a direction, and a lot of people like to just assume the positive direction. So up for positive in the vertical direction, and to the right, positive for the horizontal direction. But you can work it out by looking, or sometimes you can work it out by looking at other forces that are acting on the body. But for now, we'll just assume a certain direction or a certain sense. So the next thing to look at is the connection down here at B. So here we have a roller support. Right, so this means that at this connection here, this body would be free to move up and down. So there would be no vertical reaction there at B, but it's constrained from moving in the horizontal direction. Okay, so we'll have a horizontal reaction force there. And it's also free to rotate about this point, so no moment reaction. So just going back up here, we need to label our unknown forces or unknown reaction forces. So here I've said reaction force at A, so R subscript A in the X direction is to the right, and R subscript A in the Y direction. Right, so I'll need to make use of these when I write my equations of equilibrium. All right, so now we've got the force down here at B. Right, so it's in the horizontal direction. Again, we can try and, or we can just make an assumption about its sense, just assume it's positive, or we can have a look at the problem and see if we can work it out. So if we imagine that we take moments about point A, so this force here, this 300 Newton force, is going to tend to rotate this around clockwise about point A. Yeah, so hopefully you can see that. So if we push on this thing, this L-shaped beam, push down here, it will tend to want to rotate in a clockwise direction about point A. So for this thing to be in equilibrium, this force down here needs to push it so that we have an anti-clockwise rotation. Okay, so hopefully you can see that that force there will need to be acting to the right. So we can put that in, and we can also give it a name that we can make use of when we write our equations of equilibrium. All right, so acting at point B here, so let's call it reaction B. All right, so that's our free body diagram. So now that we have that, we can make use of that to apply our equations of equilibrium and solve for our unknowns. So let's do that. So I've just redrawn the free body diagram on the next page so that we can easily refer to it. No need for you to redraw it. We can start with any of the three equations of equilibrium. Some of the forces in the x direction equals 0, some of the forces in the y direction equals 0, and some of the moments about a particular point. But usually, for a rigid body equilibrium problem, we'll start with taking moments about a particular point. And the point that we take moments about is a point where we have at least one of our unknowns acting. Okay, so if we look up here at point A, in the top left-hand corner, we've got our two unknown forces, RAX and RAY, acting through point A. So therefore, their moment about point A will be 0. So if we write the equilibrium equation for moments about point A, they're not going to appear in the equation. The only unknown that will appear will be our unknown force RB. All right, so let's go ahead and do that. All right, so I've already answered that question. And I've already answered y point A. So writing our equation of equilibrium, sum of the moments equals 0. Now when we write this, it's very important that we put the subscript here to indicate the point we're taking moments about. Right? And also to indicate the direction that we're assuming as positive. In most of my solutions, I'll assume anti-clockwise as positive because usually I'll have x to the right. Let's quickly draw that in like this. Then, strictly speaking, the positive direction for a moment is anti-clockwise. Okay. If you don't know why, we might talk about that in another video, or go back and have a look at your calculation of moments using the vector equation. Now we want to work out our moments. And usually if we have a force at an angle, something like this, it's usually easiest to find the components of the force because usually we know these horizontal and vertical directions, okay, or often we know that. So here we know this vertical direction, vertical distance here 3, we know this horizontal distance here 2. So finding the horizontal and vertical components of this force and using Varanon's theorem or the principle of moments is usually easier for most people than trying to find the perpendicular distance of this force or this force's line of action to point A. Okay, in this case, it's not that difficult, but we'll carry on with finding the components. All right, so I've got the first one here. I've got the horizontal component of this 300 Newton force. It will be just 300 cos 50. So if we look at our right angled triangle here and use our trigonometry, we can see what that component is. And then we've also got the vertical component. Okay, so if you're not used to being able to find the components of forces, then go back and revise that. There are plenty of videos on how to find components of forces. One thing that you might note with all of my solutions, whenever I draw components, I always draw them looking like this, rather than you'll often see people draw their components something like that. Right? I tend to avoid doing that because what that does is if you put the force out here, it looks like it's acting further, if we take this vertical component here and we put it over here, like I've done here, it looks like it's acting further away than 2 meters from point A, right? So it's not strictly correct in terms of defining where the component lines of actions are. Okay, so if you're used to drawing components of forces like this, try to sometimes draw them like this and just to get out of the habit of just drawing this without thinking about it. Right, so we've got our components there. We can now start to put in our moment components that act about point A. I've just gone a little bit further ahead than I wanted to there in my solution, so get rid of that. All right, so looking at our force here, RB, we can see hopefully that the perpendicular distance between the line of action of this force RB and point A is this distance here 3. Okay, So that's what we've got up here. And is this a positive or a negative moment? As we discussed before, looking at moments about point A, this will tend to rotate the component anti-clockwise about point A. Okay, so that will be positive. Right. The next one is my vertical component here, 300 sine 50, and its perpendicular distance to point A is 2. And is it positive or negative? So if we push down here about point A, hopefully we can see that that will tend to rotate this component around clockwise about point A. Okay, so this will be negative. Okay, so we'll put a negative sign in front of that one. All right, so our next one, is there a next one? So I put equal to 0 there. Let's have a look. So we do have another force acting. It's this 300 cos 50 force here. That's the component, horizontal component of our 300 Newton force. Why does that not appear in this equation? Because its line of action, if we continue the line through this arrow here, it will pass through point A. Okay, so therefore there will be no moment generated by this force, this horizontal force, about point A. Okay, so that's why it doesn't appear in this equation. All right, so if we rearrange that, we can do our maths. We can solve for RB, and we get 153.2 newtons. If we now move to our next equation of equilibrium, sum of the forces in the x direction equals 0, and indicating here that to the right is positive. We can work our way through our forces. So we have RAX over here in the positive direction, RB in the positive direction, minus our horizontal component of the 300 Newton force here. So 300 cos 50 in the negative direction. Right? So it's important that you write these things here to justify what you're doing, and also to communicate to someone reading your solution what you're doing. Also, if you come back to your solution a week, a month, a year later, you need this here to make sense of what you've done, okay, and to be able to check it. Right? So if something happens to your design and an auditor or investigator says, show me the calculations that you did to design this thing, you're going to want to have this information here to help you interpret what you've done. So rearranging the equation, we can substitute RB from here into this equation and solve for our unknown force RAX. Okay, so next one, sum of the forces in the vertical direction equals 0. Go through this pretty quick. RAY in the positive direction minus the vertical component of the 300 Newton force, 300 sine 50, negative, all equal to 0. Rearrange that and solve for RAY, and we get 230 newtons. All right, so we've answered the question, but we shouldn't really stop there. Right? So we should summarise our final answers and round to an appropriate number of significant figures. So mostly in engineering problems, we generally don't know our input values to any more than plus or minus a few percent. Okay, so it would be incorrect of us to report our results to significant figures that indicate that we know our answer to more than plus or minus a few percent. All right, so that's why typically round your general engineering answers to 3 significant figures. Right? Unless you spend a lot of money to make sure that you know your input values to better than plus or minus a few percent, then you should round your final answers like this. When you're carrying intermediate answers through your solution, you should carry at least 4 significant figures. Right? If you're working out your solution on paper, like I've done here, calculated RB, and I need to substitute that into the next equation, right? You should be carrying at least 4 significant figures through here. through your calculations. They're my final answers. The other thing we should do is to actually check your answers. So how might you go about checking your final answers? Have a think about different ways you might go about checking your solution and your final answers. One way might be to just go through the calculations again and try and look for whether you've made any mistakes. But the problem with that is it's really easy to overlook your own mistakes. And I'm sure you've done quizzes and exams, got your answers back, or during the exam you thought you'd gone over it and said, yeah, there's no mistakes in here. You get your solution or your marked solutions back and there's a silly mistake somewhere. Usually what is better to do is to redo the problem in a different way, okay, or to partially redo the problem. You don't always have to do the whole problem, but at least partially redo the problem. I've just written down here again our answers down at the bottom here. So what I'm going to do is to think about taking moments about the point where this 300 Newton force is applied. Okay, so if I take moments about this point, right, we know that the moment of this force at this point here will be 0, right, because this force passes through this point. RAX will have 0 moment about this point because its line of action will be through that point. So we only need to look at RAY and RB. Right, so we can see that RAY times 2 needs to be equal to RB times 3. Right? So therefore, RAY should be 3 over 2 times RB. Make sense? Right? If you straighten this thing out, it's just a lever problem, right? Taking the pivot point at this location at the corner here. Right? But in this case, it's bent. Right, so RB is further away from this point than RAY is, so RAY needs to be bigger than RB. Right, is it? Let's have a look down here. Right, so RAY is bigger than RB, yep, and it's about 1.5 times RB. Right, so we can do more checks. We can go and recalculate RAX, but that's at least one check that we've done. Doesn't guarantee that we've done the problem correctly, but it will highlight a problem if there is one. Also, going through the problem again makes you think about it in a different way, and you might realise that you did something wrong in your previous solution. Okay, so that's it for that problem. Hopefully that wasn't too long. All right, so that's it for now. If you like the way I just go through these problems slowly and in more detail, please like the video and maybe even subscribe. I don't make any money out of this. Nothing's monetized for me. YouTube gets all the money. But as you probably know, clicking on like and subscribing helps with your YouTube's algorithm, and other people might be suggested my videos. If you don't like it, that's fine. Go and watch somebody else's better videos. There's plenty out there. All right. See you next time.